Good morning, guys. We'll wait for a couple of minutes. It's 11 right now, so we'll wait till 11:02 and then we'll start. Okay, guys, we'll start. Today is our second lecture on the springs. Let me just share my screen with you guys. Okay. I hope my Word document is visible to you guys, my notes. So last time I think we left at different lengths. It was kind of in quick manner. I explained basically the lengths of the first spring. Okay, so today we'll go through the lengths of the springs and then also the styles of the end. This is important to understand, and then we'll start with the equation of the spring. Okay, so before that, as I said, this is the second lecture, and in last lecture we have gone through what is spring, why spring is required, and what are different types of springs, different types of ends, uh, in the helical compression and extension spring. It is they have different purposes, like helical torsion and leaf spring, different functions depending on the functions applications we have seen for the spring, and some materials used for the spring. Okay. So today, important factor we have learned yesterday, spring index is the ratio of diameter d by d, right? Now, so we'll go through lengths of the spring. What are different lengths of the spring? As I said, if we take any spring, like this is normal helical spring, uh, it may be a tension spring or compression spring, we depending on the application. Okay. So if you take the spring, if there is no load on the spring, compressive or tensile, any load, then this length, is, like the example we are taking is a compression spring. If the load is not there, that length of the spring, total length is called as free length, right? When you put a load, the maximum load which you can put on the spring, and at that time, the length of the spring after the compression, after the maximum allowable compression is called as compressed length. Okay, and the length when the spring is in such a way that, or such a form that all the the coils are touching each other. So if you put any more load, then the load will be not taken by the spring in a torsion form, but it is taken in a direct tensile, like it will be like a solid kind of a cylinder kind of thing, and the load will be taken by the coils in a direct load. Okay, so this solid length is basically when all the coils are touching. So if you look closely to this different lengths, the solid length is basically if d is the diameter of the coil, right? Diameter of the wire, then diameter of the wire into number of coils will be your solid length, right? So this will give you nt is the number of coils, d is the diameter of the wire. Okay, now compressed length means when there is a load is maximum allowable load is there, so maximum allowable deflection is there. So delta, this length, solid length plus delta will give you the compressed length. So basically free length minus delta. Okay. So what is this delta? Delta is maximum allowable deflection. So if we know this delta, then we can find out, means basically what we are trying to say here, that each and every coil must have some kind of gap in between. Why? Because if the coils touch each other, the load will be taken directly by the coil in a direct space, and we do not want that. We want you know, spring to take the load, right? So because of that, if the gap is, what is the gap? Total gap is basically nt minus 1 into gap between adjacent coil. So if the gap between adjacent coil is, x, into that into nt minus 1. Now why minus 1? Because there is top and bottom coils, there will be only one gap, right? So nt minus 1 into gap between adjacent coil will be the total gap. Now, so free length minus this delta will give you the compressed length. Okay, or you can say this is solid length plus gap between each coil, or gap between each coil multiplied by nt minus 1. So this is the total gap. So compressed length plus total gap will give you the, sorry, solid length plus total gap will give you the compressed length, and compressed length plus delta will give you the free length. Okay, free length is equal to compressed length plus delta, and so it is solid length plus total gap plus delta, right? So it is what? This is solid length plus total gap we calculated. It is gap in one coil, gap between two coil adjacent coils multiplied by nt minus 1 plus delta will give you the free length. Now, what is the pitch? Pitch, like in threads, pitch is a distance between two successive or two adjacent coils. So if we know free length when the coil is not having any load, that length upon nt minus 1. Again, why we are taking nt minus 1? Just hold on. Hello. Okay, sorry guys, I had a call which I need to attend. So what I was trying to say is that solid length is equal to uh, basically your free length is equal to solid length plus total gap plus delta, right? So okay, we are talking about pitch. Pitch is basically distance between two adjacent coils, and now if we know the free length divided by nt's total number of coil, but top first and last coil, okay, they will have only one gap, right? If we consider that, then we have to take nt minus 1 into p will be your total, nt minus 1 into p will be your total length. So p is equal to free length upon nt minus 1, right? Now important character or the characteristic of a spring is called as stiffness of, this is most important characteristic, stiffness of the spring. What is stiffness? When we are going to put a load on a spring, right? So that time the load, if the load is p, and because of that load deflection is delta, right? So if you take this spring, if you put some load, it will be deflected. If you put more load, it will be more deflected, like that. So for a spring, this deflection is proportional to the load, right? Or opposite, load is proportional to deflection, and that constant of proportionality is called as stiffness. So stiffness is equal to load upon deflection. Are you getting my point? So if the stiffness, like if the P is the load, Newton, deflection is in mm, so Newton per mm is the stiffness. Okay, are you getting it? So stiffness is when we put load on a spring, it will get deflected, and the ratio of this load upon deflection is called as stiffness of the spring, right? So there are many names for this. We need to know that, we should know, because many places there different names will be used for the stiffness. But stiffness is basically how stiff is the spring, or if we put a load, what kind of deflection will be there in the spring. That is called a stiffness. And the different names are rate of spring. It is also rate, like load upon a deflection, so rate of the spring, gradient of spring, scale of spring, or simply sometimes it is called a spring constant, right? So these are different names for the stiffness of the spring: spring constant, scale of spring, gradient of spring, or rate of spring, right? So stiffness of the spring is a slope of load and deflection. That's why it is called as a gradient also, right? So load upon area, that ratio is called as stiffness, right? Now there was a important another important thing is active coils and inactive coils, right? So because like when the coil which is touching this external force, that will not have any kind of deflection, right? So that that's why we have total active coils and inactive coils, which is in contact with seat or in contact with force. So this active coils is equal to basically total coils minus inactive coils, right? So that will be the total number of active coils, or and total coils minus active coils will be the inactive coils. Okay. So I just wanted you to have a better feel of the spring of this rate of the spring or stiffness of the. It is very important to understand that. Okay. So I will take 2 minutes here, because I wanted it's a very basic video, but I wanted you guys to take a look at it. Okay, you guys are here. You guys can listen me, right? I'm not getting any. Well, let me just take a quickly attendance. Guys, give me some feedback whether you guys can hear me. I just wanted to make sure that you guys are not sleepy. Put something in a chat while I'm taking the attendance. Okay, you guys sharing is pause. So okay, people are saying yes, yes, yes. You guys can listen me. Okay. So most importantly, I was explaining the stiffness of the spring. That is the most important characteristic of a spring, right? So what is stiffness? How stiff? Other upon matla ki, like that person is very stiff. Kadak hai. So how stiff is the spring? Basically, it is if you are putting load, and because of the load it gets deflected. So for the more you put the load, more deflection will be there, and proportion is constant. So for that there is an experiment, okay, and with that experiment it will take two minutes to understand that, but you will get a better feel of the this thing, spring index. So let me just stop sharing this Word document, and let me just open that video, because it's awesome video, and you will get a full your concept will be clear. What is stiffness of the spring? Okay, so it's basically experiment which we can do in our lab. It's very straightforward experiment. Okay, so let me just share that screen with you. I hope now it is visible to you guys.
Materials required.
So we will be using a stand. Okay, so like basically what they are doing here, like why we need a stand to hold the spring. Then we'll use a scale. So scale will give you the deflection of the spring. We'll need spring. We need some weights. So now, okay. So this is the kind of setup. Now the spring is there, and when there is no load on the spring, it is basically a hanging field. This is a tension spring, right? So there is no load, And so basically deflection is zero this with this no load case. So the more weights you
Now,
put,
the spring extends.
it is basically going to have kind of
Put the
deflection,
reading
right?
with the pointer tip points on the meter scale. Record the reading on the scale in a tabular column. As the scale
So now they are recording for each mass or load. Mass is in kg, load is in Newton, multiplied by 9.81. We are going to take a reading of the deflection. Okay.
reading for slotted
So we
weight,
are going to put more and more loads.
50 grams
Okay.
with the tabulings
And they are
on the
going to,
tabular
now what
column.
they did is they put different masses. Okay. And for each mass, they are going to find out basically multiplied by 9.81, they will get the load and find out the deflection. Okay. Okay.
See in the record the scale moves
Again, same
upwards,
thing can be done unloading. Unloading means taking out the load. Okay. So what they have found out, they took the loading, what is the deflection while loading and unloading, and they took the average. Okay. So this will give you the approximate correct
produced
value.
by the spring from each load.
So now we have found out that for each load, what is the deflection or like the extension, means from the zero, what is the extension? And if you see closely, for each load, the deflection is going,
And
is
that's the
increasing.
value of
And the
constant
proportion
on
and
the
the
x-axis.
spring constant is basically,
Now plot a graph calculated.
okay. So spring constant is basically your load upon deflection. So if you take a load of 0.49 divided by 0.014, it will come to 35. So for each load, the more load you are going to put, it will have a proportional extension. Are you getting it? So spring constant comes to 35 Newton per meter. Okay. So are you getting it? So this is what is the spring constant all about. So let me just again go back to my word, my share word document. Okay. So, okay. So you guys clear now what is spring constant or rate of spring or stiffness of spring? So stiffness of spring is the load upon deflection. The more load you're going to put on the spring, you will have a deflection, and that corresponding ratio of load upon deflection is called a spring constant, right? K, stiffness of the spring. Okay. Okay, so I will move ahead to the next topic, and that topic is styles of the ends of the. Now, this is important to understand what are different styles of end of spring, means how the end can be there. So end can be different way. Like see, these are four examples of one is, now if you take simply coils and you do not make this end straight, right? It is as it is. Simply cut the wire at the ends. This thing is called as plain ends. Okay. Now, in the second one, same thing is there, but you have with a grinder, you will be grinding it and making it horizontal. So that is the second case, where ends are plain, but those are ground. Means now here, if we put a load, it will have a point contact. But in second case, it will have a surface contact, right? So first and second is almost same. The only thing in second case is the ends are grounded to make it a plain surface. Now in the third case, it is the end is not like this. It is not inclined. We bend the end of the spring and make it horizontal. Now, so again, the second case will have, third case is basically it will have a surface contact with the end, and it will be able to take the load better way. And in the last case is the again modification of case number 3, where we are grounding the ends to make a proper better surface contact. Okay, so these are the different types of ends. And now how we take the total number of active coils? If it is plain ends, then start and end will have equal distribution of the load. So it will take total coils as total number of coils. Okay. So whatever coils are there total, say if there are 9 coils, we'll take total number of active turns is as 9 only. Now in case of plane, if you take the plane, by considering two ends, half of the coil will not be active. So that time we'll take nt minus half as the plane ends with the grounded. Okay. But now with the square ends, if you take square, so the ending, the first and the last, top and bottom coil will be in contact, completely in surface contact with the your object, and because of that, it will not have any kind of active participation in the spring action, right? So because of that, we will reduce those two. So the total number of active coils will take nt minus 2 in case of square ends and square and ground ends. Okay, are you getting it? So in the example or in the problems, you will be given what kind of ends are there. So if it is plain ends, take total number of coils as equal to total number of active coils. So plain ends will be grounded, nt minus 1 half is equal to your total number of active coils. And for square and ends which are maybe normal or rounded ends, it will take nt minus 2 as your total number of active coils. Okay, clear? And now last portion, how does basically end style means, so at the end of the coil you might have some kind of, so this is for the extension springs, this is for the compression spring, and this is for the extension spring. The extension spring will obviously need to have some kind of hook kind of provision to put the load at the end of it, or how to put it in a tension. So they might be V hook or rectangular. Only shape of the hook is changing. So V hook, rectangular hook. It may be a full hook like a circular. This one we use a lot. Or extended means a circular hook, but it will have some kind of extension for the length. Okay. So these are the how the ends will look like in case of helical extension spring, and these are the ends which we will fix in a helical compression spring. Okay. Clear? So now we will go ahead with the basic finding out the stresses and deflection of a helical spring. Okay, but till now is it clear, you guys? Everything is clear. I will quickly go through the basic concepts. You guys have any doubt? Kindly ask me in a chat. So we have seen the springs, different types of springs, and functions of the springs, materials of the spring. We have seen some basic characteristic of the spring or terminologies of the spring, inside, outside diameter, or diameter of the wire. We have seen spring index, capital D upon small d, ratio of the coil diameter upon wire diameter, right? We have seen lengths of the springs, free length, compressed length, and solid length. Then we have seen stiffness of the spring, very important characteristic of the spring, and the styles of the ends. Okay, so if we have this basic knowledge, we can go ahead with the design of the spring. Okay, so you guys want me to go ahead with the design of the spring? Okay, you guys are all following me whatever I'm saying. So if that is the case, then I will simply go ahead with the deflection of the spring. Okay, like what is, how to calculate stresses and deflection of the spring. Now this is very what you can say, a critical part where you need to understand how springs work. If we can understand this, then it will be very easy for you to follow how this design is. Design is very simple. It is not very high-fi or any complicated thing. Now see this, I have shown here a spring which is basically, if you see the loads are going away, so it is a kind of helical spring which is a tension spring. Okay, it might be where it might be helical compression or tension spring, doesn't matter. But the stresses in the coil, if you see, like generally, as we have talked about it, the stresses in the coil not be direct tensile or direct compressive stresses. The stresses in the coil will be a different kind. Now, how these stresses will be now, as I said, there will be a torsion or the twisting of the spring coil happens, and because of that, there will be shear because of the twisting moment. Okay. Now, how this happens? Now, see, we are putting a load P at the end. Now, this load is acting at some distance from this wire, right? If it is say D is the diameter of the coil, so then it is acting at a distance D by 2. If you see this first diagram, okay, let me just increase the size of this. Okay, now in the first diagram A, the load P is acting at the center of the coil, right? That is what we are assuming it is acting at the center. So it is acting at a distance D by 2 from the coil, right? From the center of the wire. Okay, so because of that, now it will have a moment, twisting moment. So what is the value of twisting moment? P into D by 2. That will be the twisting moment. And because of that, what happens? It will not be, if you take a rod, okay, take a rod, straight rod, okay, and try to put a load on that. So that rod will undergo compression, or if you pull it under or tension or compression, but that will be direct load P upon area, right? But this is not the case here. We are not in the rod, we are not putting direct tensile or compressive stresses. What we are doing, we are trying to twist it. So how to calculate that? Try to unwind this coil and make it a rod. Okay. So if we unwind this coil and make it a simple plain rod, it will look like in a diagram B, right? So where the P is load applied at a distance D by 2. So because of that, there will be a moment or the twisting or the torque P into D by 2. Same thing is applicable on the other side. And because of that, this rod will be having a twisting action. We will try to rotate it. Means it will try to, both will have opposite kind of torque. So it will have a kind of twist, or we call it pida. We'll try to twist it, right? So because of this twisting, we will have a shear. And how to you calculate? We are going to use a simply twisting equation, okay? And with that, we can calculate the shear in the coil. But are you getting? We are not going to use direct stress formula because the coil will not undergo direct stress. It will undergo stress, shear stress because of the twisting, okay? So now, if we have followed this, then we can go ahead with the how to calculate this stress and how to calculate the deflection, right? Now, what is most important to remember? The twisting moment in the coil is P into D by 2, right? And now, if n is the number of coils, right? So then what is this length of this wire will be there? So for one coil, one round of the wire, we will, if this is the diameter, pi d will be its perimeter, right? So P pi d into n is number of coils will be your total length of the wire. Okay, I will repeat. If we take only one coil, take a single coil. Okay, so now what is the length of that wire? It will be pi into d because d is the diameter of the coil, right? So pi into d will be the perimeter of this coil and that will be the length of the wire. And that multiplied by number of turns, pi d n will be total length of the wire. Okay, so now we know what is total length of the wire, pi d n. We know what is the moments acting on that wire, P into D by 2. Then we can go ahead with the design of the coil. Okay. Now, how this design is done? Now, moment is PD by 2, right? We have seen that. Now, if we use a torsion equation, okay, okay, MT, M upon I is equal to, M upon J is equal to G theta by L, right? What is the equation of tau upon J is equal to, tau upon J is equal to T upon R equal to G theta by L. That is the equation of the torsion, right? So tau here, tau means basically T upon J. T is torque. Here we denoted, we generally denote it by symbol MT. So T upon J, that is MT upon J is equal to tau upon R is equal to Z theta by L. That is the torsion equation. So if we take T is equal to tau is equal to T upon R, MT upon J into R. MT upon J into R, R is equal to D by 2, MT upon J is equal to pi by 32 D raised to 4. So we will get this equation. You must be remembering this equation, or if you don't know, then you should know this equation. We have got this equation by using MT upon J is equal to tau by R is equal to Z theta by that equation. Okay. So shear stress tau is given by 16 MT upon pi d cube. Now we know MT PD by 2, right? So we will get shear stress in the coil is 8 PD upon pi d cube. So we know that the shear stress can be used calculated by using torsion equation, and we get shear stress in a coil as 8 PD upon pi d cube. Okay. So now we know shear stress. Okay. So now there will be a, obviously, like if you know this kind of load are there, this is a shear stress because of the twisting or the torsion, but also because of the direct load, there will be also shear, right? So now we have to calculate, there will be kind of receive, there are two stresses, the stress because of the shear. Now this shear will be 0 at the center, maximum at the outside. Direct shear will be uniform throughout. So if you combine these two, the resultant shear will be like this. Okay. Again, I will repeat this. If the A will give you the shear because of the twisting, right? It will be maximum at the end, extreme fiber, 0 at the center. The direct shear will be equivalent or the equal at all places from extreme fiber to the inner fiber. And if we combine these two directly, because both of them are shear stresses, we can directly add them. We'll get this is the stress in the coil, right? Now for the direct shear, there is factor is something called as Ks factor of for the account of direct shear, and Ks is the factor for the stress constant. Now because of this, you know, we are bending a wire and making giving it a curve, and because of that now it is having a circular shape, right? So because of that, there is a obviously stress concentration will be there, and the factor is called as Kc, right? So this the multiplication of this factor, we will get a case for the K factor for combined effect of the two factor. Two factor is what? Stress concentration factor and direct shear factor, right? So because of that, we will use combination of these two and we'll use a factor called as K. Now what is direct shear? Direct shear is P upon area, load upon area, right? What is the area of the coil? Pi by 4 d square. So direct shear will be 4p upon pi d square, right? So now we have the first stress is what? Shear stress because of the torsion or the twisting, that is 8 PD upon pi d cube, right? We have seen that. And because of the direct shear, it is 4p upon pi d square. Now we want to make, or we want to have this kind of factor 8pd upon pi d cube. So what we can do, we can say this is 8p multiplied by d divided by d. So we'll get 8pd, and now here also pi d square, so we'll make it pi d cube, so multiplied by that by d. But since it is 4, to make it 8, we will multiply by 0.5. So this whatever you see in the bracket, it is just a multiplying factor to this 4p upon pi d square to make it 8pd upon pi d cube. Now why do we want to make it 8pd upon pi d cube? Because the twist shear because of the twisting is 8pd upon pi d cube, and we want to combine these two, so we want to have something in common, right? So what we will have common? 8pd upon pi d cube. Okay, so we'll take 8pd upon pi d cube, so we have to multiply that by 0.5 to make 8 to 4, multiplied by that by d small d to make pi d square cube to pi d square, and divided by d to cancel this d, right? So we'll get 8pd upon pi d cube, and this 0.5 d upon d will be your multiplying factor. Now what are the combination? Because of both of them are direct the shear stresses, so we can combine torsion shear stress and direct shear stress to have total stress. The total shear stress is 8pd upon pi d cube. This is because of the twisting, and 8pd upon pi d cube into 0.5 d upon d. So we'll take it out, and this in bracket will have 1 plus 0.5 upon 0.5 d upon d. Now we also know that capital D upon small d is spring index, right? So we have seen that right here, ratio of coil diameter, right? We have seen here ratio of spring index C is coil diameter capital D upon small d, right? Coil diameter upon wire diameter. So if we can replace that here, right? So we will get it is 0.1 plus 0.5 upon C, right? Right? This Ks, this is Ks is now we have seen here. This Ks is a factor due to direct shear, and now also there is factor due to curvature, right? So tau is equal to K into this, because of the curvature will take this K is equal to Ks into Kc, right? So K into 8pd upon pi d cube. Now this K is called as wall factor, and the wall factor K is given by 4c minus 1 upon 4c minus 4 plus 0.615 upon C. Now the derivation or the equation of this not in syllabus for you guys, so we have to simply remember it. What is wall factor? It is a factor K which we use to multiply 8pd upon pi d cube to get a shear stress in the spring. What is this value of K? K is equal to 4c minus 1, 4c minus 4 plus 0.615 upon C. C is spring index, capital D upon small d, diameter of the coil upon diameter of the wire. C, use that C in this equation, 4c minus 1 upon 4c minus 4 plus 0.615 upon C. We will get to K, and use this K to multiply it by K 8pd upon pi d cube to get shear stress in the spring. Okay. So that is how we will calculate shear stress. Now we will be given allowable stress for spring, right? Then that allowable stress multiplied by 0.5 will be your allowable shear stress, and then multiply that, or we can equal that to K into 8pd upon pi d cube, where K is wall factor given by this equation. And with this you can, if we know the load, if we know the coil diameter, then we can calculate the wire diameter. Okay. Okay. So you guys are following whatever we are saying. So now the last part of this design part of this normal or helical spring is finding out the deflection of the spring, right? Or the angle of the twist. How much your twist of this, your wire will be there. Now this is again, we'll use the same formula of torsion. Mt upon J is equal to G theta by L. I told you we are going to use both the parts of this equation. Mt upon J is equal to tau upon R is equal to G theta upon L. That is a twisting or torsion equation. So theta is equal to MTL upon JG. Now MT upon J is equal to G theta by L, right? So MT we know twisting moment PD by 2. L is the length of the bar pi dn, and J is pi by 32 d raised to 4, and G is your modulus of rigidity, right? So we know all these parts of all different components of this equation. Theta is equal to MTL upon GJ. So we'll put all those value. This is MT PD by 2. Pi d is your length of the total wire. Pi by 32 d raised to 4 will be your J, polar moment of inertia. So we get 16 PD square N upon G d raised to 4. This is the twist of the end of the spring. Twist means how much it will be rotated. Now we have to find out the deflection delta. Now delta is equal to what? If you see this here, delta is equal to your this length of this what you can say distance of this load from this from the center of the wire multiplied by angle theta. We have just calculated theta as 16 PD square upon PD square n upon GD raised to 4. Multiply that with this length. What is the length? D by 2. So theta into D by 2 will be your deflection of the spring. So delta is equal to this, again this is multiplied by D by 2. So this is PD. This 16 will become, because it is D by 2, so 16 will become 8. 8 PD cube n upon GD raised to 4. So deflection of a spring is given by equation 8 PD cube n upon GD raised to 4. How we calculate that? Delta is equal to theta into R. R is the distance of the load from the center of the wire. So it is D by 2. Theta 16 PD square n upon GD raised to 4. We calculate that by torsion equation, right? So now we know deflection of a spring is given by equation 8 PD cube n upon GD raised to 4. Here P is the load, D is the diameter of the coil, n is number of coils, G is modulus of rigidity, and small d is the diameter of the wire. Now since we know P, so we can find out the rate of the spring or the stiffness of the spring as P upon delta. We just know that load upon deflection is your stiffness of the spring. How stiff is the spring? So we put it this value of delta here, and we get P will be cancelled, and we will get GD raised to 4 upon 8 D cube n. This is the spring stiffness of the this is the stiffness of the spring, right? GD raised to 4 upon 8 D cube n. So stiffness of the spring is given by formula G modulus of rigidity, D raised to 4 diameter of the wire raised to 4 upon 8 D cube n. D is the diameter of the coil, n is number of coils. Okay. Right. Now with this equation, we will get to know that G is the modulus of rigidity of the wire. It is fixed. D is the diameter of the coil. Right. So, basically, if you see this, it will get this equation diameter of the coil and it is number of coils. So if we know any one of these, or if we know the spring index, we can calculate the diameter of the wire. If we know the diameter of the wire, we can calculate the radius of the coil and all that. So we can, do this, all these calculations, and we can find out different, what you can say, dimensions of the spring. Now with this, we know that delta is proportional to P, or P is proportional to delta, right? So actually, again, this E is given by area of a triangle. If we put this load upon deflection, this is called as load deflection. So the more deflection load we are going to put, will have more, if what you can say, deflection, because it is directly proportional. So this E is basically energy stored in the spring. Now what is energy? Load into distance into half. So half into the area below this diagram, or the area below this line, is called as the energy stored in the spring. That is given by half into P into delta. So P into delta is load into deflection multiplied by half will be your the energy stored in the spring. Okay. So this is how we will do the design of the spring. Next time we will try to get an example or possible series and parallel connections. Now there are few conceptual part also left. So if possible, we'll take a numerical as well as we'll try to go through now next lecture series and parallel connections. Now in springs we can put the two springs in parallel, or they in series, one after another. We can put two springs, and for this now we have to calculate the ultimate or the resultant stiffness. We'll see now how to do that in a next lecture. Okay, but is it clear now what is basic design part? Now for the basic design, we must know the spring index. We need to know the stiffness of the spring. We use the torsion equation, but basically the stresses developed in a spring are the shear stresses. Two parts. First is shear stress because of the twisting, and direct shear. Shear stress because of twisting is given by the equation 8 PD upon pi d cube, and because of direct shear it is given by 8 P upon pi d square. So basically it is 8 PD upon pi d cube into 0.5 D upon D. So we'll get combined total shear stress as 8 PD upon pi d cube multiplied by 1 plus 0.5 upon C, right? And so that is the total stress. So, and if we have to consider stress concentration factor and all that. So we'll get T is equal to K into 8 PD upon pi d cube, where K is Wahl's factor, and Wahl factor is 4C minus 1 upon 4C